So sagittal, I love words and their origins. Does anybody know the origin of the term sagittal? How about what is in the astrology world? What is Sagittarius? Yeah. What is Sagittarius? The centaur, right?
And in Italian, it's the same.
Yeah. So it's the centaur with the bow and arrow, and sagittal refers to the arrow part, or to the act of shooting an arrow. So it's that cut from a bow, right? I'm holding a bow, a sagittal plane, and you can have a mid-sagittal plane. Again, I love words. Too much, not simple enough. Mid-sagittal, not mid-sagittal. I like longitudinal and I like transverse. I like short axis and I like long axis. But you'll encounter people who want you to say mid-sagittal, for example. So this is a fairly mid-sagittal cut of the body. Does anyone know? I was about to say, does anyone know what we're looking at? It's labeled on the screen. So one of the orientations we'll lay onto this is where the beam is coming from. So this is a direct mid-sagittal shot. And we've got the belly and the back and the head and the feet. And over time, you guys would be able to look at this shot and you wouldn't need anybody to tell you where the head and the feet are, because you would know that the aorta is deepest in this part of the body and becomes more superficial as you run inferior. You would know the SMA runs down, and it's the SMA that's the tiny dark stripe that's coming out there. And then those same part of the body, it's a little too fast, you go and you turn to a transverse orientation, and it's going to look like this instead. You're going to now not just be over the circular aorta with the SMA as that smaller circle up there. You're going to get the IVC in view too. So again, the language that we use is about the properties of the probe. It's about the properties of the tissue the probe is shooting through. It's about the properties of the sound. We're going to use terms to describe the picture that you're seeing in terms of some physics issues like anechoic, hyperechoic, hypoechoic, and we're going to talk about the orientation of your probe using transverse, longitudinal, using short axis and long axis of the organ. Okay, so going back to the machine and trying to decide how I translate all of this stuff into machine operations. You know, when you're driving a car, most of us are right-handed. So a lot of what you end up being asked to do in terms of operations of the car are things with your right hand, right? You're going to reach here to do important stuff, like indicate which way you're going, like operate gears, put the car in reverse, that kind of thing. And so it's the same on machine. The most commonly used stuff, kind of top right. If I was teaching like the very basics of driving, I would teach someone how to turn on the car, teach you how to turn on the machine. I teach you to make it go forward and to use the steering wheel. And I think the equivalent things in using an ultrasound machine, yes, turning it on, but then gain and depth are probably the two biggest things. And then like switching between different probes and applications, which is like switching gears. So you'll see in the top right here, we have the ability to choose between transducers and exam types. Awesome. Like, yes, I want to go and use a linear probe. I need to know where to do that. We have this button called B in 2D, which is frustrating. And we've gone on our machines and labeled gain. That's what that button is. I talked about how there was A mode ultrasound, which didn't produce a visual image. So when they made grayscale, like, hey, there's an actual picture of what's going on, they call it B mode. We're stuck with all of this bad language, right? Turn up the B mode gain. Just turn up the gain. And then you'll see also the button for depth. So everything that you really need to start driving is in that upper right corner. And depth is all about the machine's processing power. So if I want the machine to really focus on a given area, and I say like, look, I'm interested in the first 3 centimeters, it can do that. It can produce more accurate images of those first 3 centimeters by ignoring processing everything deep to that. And when I set my gain on the screen, that's all I'm really doing for the machine. Yes, it's going to look a little bit magnified, but it's not just the machine cuts out the bottom and still processes it. It doesn't even bother processing the bottom. So setting your gain right really does help produce better images by allowing the machine's processing power to focus where you want it to focus. So here's just an example of like, that's the bladder. Does that give me all the information I want? No. So there's the person adjusting the depth in real time to catch the bottom of that bladder wall. Especially in emergency medicine, we care about that area of the pelvis a bunch. So back to our top right corner, and you find that gain button that's labeled gain on their machines, but 2D is often, sorry, B mode or the 2D gain is the other term you'll find. Gain is just another name for volume, essentially. And these two images are just the same thing. On the left, I've got higher gain. On the right, I've got lower gain. So it's kind of signal to noise. It's like volume of a speaker. Turn the sound up really loud, you're going to get more artifact, right? You're going to get buzzing, you're going to get shaking. Turn it down too low and you're not going to be able to hear everything you want to hear. So different people have different preferences, how high they like their gain. I'm a classic over gainer. I like my gain turned really high and I tolerate the artifacts, and different people have different tastes. We'll quickly go over these 5 common artifacts because we've already discussed them in some depth in the textbook. So shadow doesn't need a lot of explanation, right? Anybody know what organ we're looking at here? So we got a kidney, a dilated collecting system, and that bright white structure with fairly sharp dark shadow dropping from it. So that's our irregularly surfaced stone that's not letting the beam through. And then edge artifact we described as the idea of a perfect tangent, right? If you don't actually have a reflective surface, you can't reflect. And it's something we practically see with a liquid substance within something more solid. So when the beam hits just that edge, it can reflect everywhere except back the probe face, so you just get dropout signal from that one spot.